All right, I want to correct with you guys one last question that's on the homework sheet, and that is from Ibid. Before I do, I'm going to share my screen here and show you that for Ibid, I want to remember that all of the solutions are available in a PDF format. Here we're looking at the solution for exercise 4.1, number 8. Where did I get this? Well, if you go to our page under classwork, you'll notice there's a class drive folder. And if you click on the class drive folder, I've loaded up a couple of things in there, including the full solution manual to the Ibid textbook. Okay, it's coming up here in a second, and you'll see it. You just choose the series and differential equation folder. A little bit slow today. Here we go. And then you pick the right chapter. And once it opens up to the right chapter, you go to the proper exercise and you'll see the solution. Okay? Now, what I want to do is to answer this question for you guys. And so I'm going to share now the iPad. Okay? And let's take a look at this solution here. So to do this, we want to use the Taylor polynomial for sine x to deduce a Taylor polynomial for sine x squared. When you see that, anything with sine or cosine, e to the x, or tan, you don't actually do the Taylor polynomial, or in this case, the Maclaurin polynomial, because it's around x is 0. You don't actually do that by derivatives, okay? That'll be really complicated. If you start differentiating sine, you'd have 2x times the cosine of x squared, so then you'd have a product rule, the next derivative on. No, we don't do that. You just use your polynomial for sine, so that's like it's x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. The general term is so these three terms here are in the formula booklet, so you can always look those up if you're in doubt, as I was there for a second. And then the general term, we've got to figure it out from the three terms that are giving. Well, you can see they're odd factorials on the bottom, so I believe we should probably go 2n minus 1, so that when n is 1, we pick up 1. And then this is the same power as the odd number on the bottom, and then we have to put a negative 1 there. It needs to alternate, and it needs to start with negative, so 1 will work, and a negative 1 to the n will work, because when n is 1, we get a negative, and that's the general term, okay, for sine x. Now, if they want sine of x squared, we've done this a number of times already, you just do like a composition of function, right? So it's x squared cubed over 3 factorial, x squared to the 5 over 5 factorial, x squared to the 7 over 7 factorial, and the general term is x squared to the 2n minus 1, 2n minus 1 factorial, okay? So if we simplify, it's x squared minus x to the 6 over 3 factorial, x to the 10 over 5 factorial, minus x to the 14 over 7 factorial, general term x to the 4n minus 2 over 2n minus 1 factorial, okay? And that's part A, okay? That's part A. Now part B is kind of a weird question. It wants you to split this up into these terms and then the rest of the terms are n. Now this isn't to be confused with the, which I did originally actually, I confused this with the remainder that is in the Taylor's theorem, okay? So let me show you what I'm talking about. So let's go back to those notes that we had on Taylor's theorem. You see, they don't mean this remainder. I thought they did. I mean, and they could really, but if I look at this, when I looked at the solution, I realized that they actually wanted something else, okay? So don't worry about that for exam purposes. It'll be made clear what exactly we're looking for when you're given the exam question, okay? So let's go back to this problem here we're trying to correct. So if you look at the solutions, what they really wanted you to do is just split this up in part B So they want you to split f of x into the first terms until n is 7. Now that's kind of weird. They don't mean when, let me point this out here, when this n is 7, in which case down here we'd have 13 factorial. They mean when this bit here is 7. Again, that would have to be made clear, more clear in the question, which Ibid unfortunately didn't do. Okay, so what we're actually going to end up with here is x to the 7 minus x to the 6 over 3 factorial, x to the 10 over 5 factorial, minus x to the 14 over 7 factorial. So that's what they mean by n is 7. And then the rest of the stuff would be everything else. So what's left over? Well, we'd have our expression here. That's x to the 4n minus 2, 2n minus 1 factorial. But n would start off with, in this particular case, this would go, oops, can I undo that? Yeah, n would go here, 1, 2, 3, 4. So it would be n is 5 to infinity. Okay, so this would be the, I believe they called it Pn of x squared. And this would be Rn of x squared. Okay, nice. So question C now says, this thing will move for me. The words, part C says to show that this definite integral would be equal to this sum plus the error. And by the error, they mean the integral of all of these things here. In other words, this integral of this expression Rn of x squared when n is 7. So to do that, we have to go 0 to 1 sine x squared dx would be the integral of all of this stuff over here. I mean, we're going to split it up into the integral here, the integral of the polynomial part, plus the integral, the definite integral of the error part, which we're going to leave undone as per the question. Okay, so what we have is 0 to 1 x squared, x to the 6 over 3 factorial, x to the 10 over 5 factorial, x to the 14 over 7 factorial dx, and then 0 to 1, we're just going to write the integral of this part as r7 x squared dx. Okay, and that's the part that's left over. So really all we have to do is do this integral over here on the left. Let's leave a bit of space here, and then we can do that. So what's it going to be? Well, it's x cubed over 3 minus x to the 7 over 7 with the 3 factorial down there, x to the 11 over 11, 5 factorial, x to the 15, 15 from 7 factorial between 0 and 1, plus we'll just call this error so we don't have to write all that notation out every time. Okay, you can see when we go to evaluate this expression over here, we have to substitute 1 in there, which will make all the x's to different powers equal to 1, and then 0, and when we put 0 in here, the whole thing is 0. So the evaluation of this is 1/3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial minus 1 over 15 times 7 factorial minus 0. And is that what they want us to show? Yes. There you go. There you have it. Plus the error. And we've already identified the error here as the definite integral between 0 and 1 of r7 x squared. Okay, so that's part C. And then part D of this question says, the words that are missing here are show that. The error involved is approximately equal to this bit here. Okay, and then correct the 4 decimal places. We want to show, therefore, as a result, that this definite integral is equal to this bit plus the amount over here. So we want to look precisely at that error term for this question. So the error at this point, oh, we're going to need a new page. Let's put in a bit more room here. Where exactly we are writing right there, add a page. Okay, so the error at this point, what we have is 0 to 1. This is, let me just make sure we're doing this. Yeah, we want to show that the error involved in C. That's right. The error involved in C is r to the 7 x squared dx. Okay, and if you look at that, that would be the integral from 0 to 1 minus 1. Excuse me. Nice. I mean, the summation as n goes from 5 to infinity of minus 1, x to the 4n minus 2 over 2n minus 1 factorial. Okay, so that error is the integral of an alternating series. Okay, so if we think about our test for alternating series, we know that the error term, let's just back up so we can remind ourselves, we look back at the alternating series notes. Okay, we know that the error in the alternating series is right here, is always less than a to the n plus 1. Okay, so the error that we're looking at is smaller than the next term that's left out in the approximation to the alternating series when n is 7. Okay. Okay, don't know if you noticed there, but I just took a pause to the video because I was a little bit confused for a moment there in terms of what Ibid had put into their solution manual. And even though I gave it a big plug at the beginning to look in their solution manual, turns out that their solution isn't totally 100% correct. Let me show you why, if I can, just for a second, go back to the desktop. Okay, and show you what I'm talking about. So they mention in here, that full screen, they mention in here that as the series is alternating, the error r to the n in absolute value is less than or equal to the next term, and then they just plug this in here. But they haven't really listed the series because the error is not really an alternating series. It is an alternating series, but only once we take the integral. So I'm going to expand on their answer D in my notes in just a second, but it'll be very similar to what they've written down. We'll get the same answer, but in kind of a slightly different way. So let me go back to the iPad here. Oops, I didn't mean to stop that sharing. Hi, everybody. How's it going? What I meant to do is change over back to the iPad, and here we go. Okay, and so we go back. There it is here. So we want to keep this little result here in mind. So if you can keep that in your mind, let's go back to correcting that problem. And so why don't we go back to the actual thing that we were trying to do. I'm going to say that what we want to do is 0 to 1 sine of x squared dx. Well, the full value of this would have been 0 to 1 x squared minus x to the 6 over 3 factorial plus x to the 10 over 5 factorial on and on forever dx. And if we were actually to do that, we'd see that we'd have x to the 3 over 3 minus x to the 7 over 7, 3 factorial. So I'm just going to take the definite integral here, okay, but not splitting between an approximation here, but I'm actually taking the definite integral of the whole thing. So having done that, and this is evaluated between 0 and 1. Now that's important because the 1s mean all the x's to the different powers are 1, and the 0 means everything that when you put 0 in is going to give you a 0. So what we end up here is a third minus 1 over 7, 3 factorial, plus 1 over 11, 5 factorial. The next one would have been 1 over 15, 7 factorial, and that would have been subtraction. Sorry about that. The next one would be addition, and it would have been 1 over 19 with a 9 factorial, and so on and so forth. And then, of course, the 0, it's subtracting 0, so it's as if you're not subtracting it at all. So our approximation, because the question was asking us, we go back to the question for a sec, to show that the error involved with this approximation is about this number here. Okay, so to do that, let's say that this thing is actually equal to this first bit. So 1/3 minus 1 over 7, 3 factorial, plus 1 over 11, 5 factorial, minus 1 over 15, 7 factorial. That's our estimate, plus the error. And the error part is 1 over 19, 9 factorial, minus 1 over, the next one would have been 23, 11 factorial, so on and so forth. So we have the estimate, which are these first 4 terms, plus this other bit on the end, which is 1 over 19, 9 factorial minus 1 over 23, 11 factorial, so on and so forth. The whole thing, as you see, is actually an alternating series in the form of n goes 0 to infinity, and we have 1 over, okay, so what did we do? We have 1 over 2n plus 1. What we took was 2n plus 1. That's our 4n minus 1. Okay, so let me highlight this. The 3, the 7, and the 11 are all found from the formula, 4n minus 1. Why 4n minus 1? Well, you would take your 4n minus 2 up here when you integrate it and add 1 to that, and that's why we were dividing every time by 4n minus 1, okay? And then you have a 1 on the top, that stays the same. And then next to here, this other bit would have been the 2n minus 1 factorial. 2n minus 1 factorial, okay? So that whole integral is actually, with one last thing, our alternating aspect, which is minus 1. And we want to start out positive, so we can just put an n there, because n is going from 0 and on. 0 and on. So I believe we want 2n plus 1 if we're starting at 0. Okay, so let me just recap that, make sure we got this right. Yeah, 0 gives me a 3 here, but it gives me a 1 factorial there. And this starts off positive. The next time, when n is 2, we're going to get 8 minus 1 is 7, that's correct. And then when n is 2 here, when n is 1, excuse me, we're going to get 0 is 3 factorial. I think we've messed this up, hold on. When n is 1, I think we just wanted 1. That will give me 3. And then here we need 3 factorial. Then we need 0 factorial. So the solution is, sorry, I'm a little finicky with the ends here. This is a 1. And this bit here is 2n minus 1 factorial. That should be working for us. Let's see, when we go to 3 here, we're going to get 12 minus 1 is 11, and 6 minus 1 is 5 factorial. Perfect. Okay, so as you can see, the actual value for this definite integral is in fact an alternating series. And so the value of it, the error, so it would be this approximate, the estimate plus an error. And we know by the alternating series, the theorem of alternating series, that the estimate is less than the next term. So it was an plus 1. Well, if we went only up to, whoops, do that. We only went up to this term here, the error would be less than this amount right there. So that would be 1 over 19, 9 factorial. So I guess that, I'm going to really go on a limb here, would be, no, the n wasn't 7. I shouldn't have done that. It would have been, this one here is coming when my n down here is 4. So in this particular case, it's a 4 plus 1, and this bit here is a 5. And if we evaluate that number there on our calculator out here for a sec, sorry about that. The calculator out here. Okay, so we have to evaluate 1 divided by, in brackets, 19 times 9, math factorial. We get that number there, okay? And so that number is actually equal to 0.70, right? So I gotta move the decimal place over 7 times. So 1 time moves it over for the 1, and I gotta put 1, 2, 3, 4, 5, 6, 1, 4, 5. Okay, so a to the n is less than that amount here. They want it less than 1, 2, 3, 4, 5, 6 zeros. Is that right? One, who can see that? 1, 2, 3, 4, 5, 6 zeros, 1, 5. Okay, and you can see that's exactly what we have. Okay, that's less than, even less than what they want. Because I think all they've done is rounded this to that particular number there. Okay, so as a result, it took a long time. I had to be really careful with that answer. As a result, you can see the last part follows immediately. That is correct to 4 decimal places. This number here is coming from just evaluating our estimate above, which you guys can do on your calculator, to that many decimal places. Okay? Kind of a long answer, but be careful when using the solution manual. Make sure you understand what's in there. If you don't understand what's in the solution manual after I post them, please just send me a message and we can have a chat one-on-one in the coming weeks. Okay?